In this lesson, we're going to look at inverse functions. And basically what inverse functions are they're the functions that undo a regular function. So when you're looking at inverse functions, it's kind of like comparing f of x to this f inverse of x. So notice the notation, you have f to the negative 1 of x. The negative 1 isn't a power, it's just representing the inverse. So I think of inverse functions as kind of like you're doing and you're undoing. So it's kind of like a do and an undo process. So basically what that means is if I have, let's say, some example, so let me give you an example. So we're going to let x equal 2. And let's say I have these two functions. So I have f of x equals 2 plus x. And the inverse of that function is x minus 2. So then what happens is if I take this 2 and I plug it in, so let's say I have f of 2 would be 2 plus 2, which gives me 4. So I plug in 2, I get out 4. So then what happens with the inverse function, it means that if I plug in 4 into this inverse function, I'm going to get out 2. So if 2 is the input and the output's 4, the inverse is just the opposite of that. So let's just take a look. So if I take and I plug in 4, 4 minus 2 gives me 2. So this, I input, I get out 2. 2 is the input of this original. So it's basically like you're plugging in, you get out an output, you take the output, you plug it back in, and you get out what you started with. So it's undoing that whole process. That's really what an inverse function does. A couple other things to note here. Inverse, when we say inverse function, that means it's a function. However, you could have a function and you could take the inverse of it, and what you get out might not actually be a function. So that's something that we should make a note of. So the inverse will always be a relation, but it may or may not be a function. So it may or may not be. So in which case, if it's not a function, that means you can't use this inverse function notation. You would simply just have to use y equals so that it's known that it's a relation. So that's the difference here. So the inverse of a function, there's two different things that when we talk about this, finding the inverse of a function means that the original was a function, but it doesn't necessarily mean that what you get out is a function. So the inverse of a function may not be a function. But if we say, so versus the inverse function, so this is the inverse function, I'm calling what I get out a function, that means that it is a function. The result is a function. So just a couple of things to kind of take note of when we're doing this. So what happens now is looking at how do we actually find the inverse. So there's two different ways. There's ways to find the inverse of a function algebraically, and there's ways to do it graphically. So I'm going to kind of model both ways to you. So the first thing here is this example. We want to find the inverse of this function. So algebraically, we'll look at first. So basically, to find the inverse algebraically, we're going to go through this three-step process. First thing you're going to do is you're going to set the function equal to y, which in this case it's already equal to y, but I'll just rewrite it. The second thing you're going to do is you're going to swap the x and the y values. So x becomes y and y becomes x. So I'm just going to switch those. And then the third step is to solve for the new y. So now I have y over here, so I need to get y by itself. So I'm going to subtract 5 from both sides. So we get x minus 5 equals 2y. I'm going to divide everything by 2. So we get 1/2 x minus 5 over 2 equals y, or y equals 1/2 x minus 5/2. So this would be my inverse of the original function. Now, because I know that this is the shape of a line, and I know that all lines are functions, I can rewrite this using the inverse notation, since I know that the result is a function. So either one of these would be the correct answer. So now the question is, how do we do this graphically? So graphically, means we're going to start by graphing the original. So we're going to graph y equals 2x plus 5. So my slope is 2 over 1, which means up 1 or up 2 over 1. And the y-intercept is 5, so you're going to start at 5, up 2 over 1, up 2 over 1, then reverse that process. And just so that you get enough points, and then you can go ahead and connect those. So that's going to be the original. So I'm going to put arrows on that, and I'm going to label it so we know that that's the original. So this is y equals 2x plus 5. And now what we're going to do is we're going to reflect this function over the line y equals x. So what that means is the line y equals x, remember the slope would be 1 up 1 over 1, and it starts at y, or the 0, 0 is the y-intercept. But really this is just the diagonal line that goes through your graph from corner to corner through the middle, because it's up 1 over 1, up 1 over 1. Y equals x is all of the points like 1, 1, 2, 2, 3, 3, 4, 4. So this is the line y equals x. And what we want to do is we want to take this line and we want to reflect it over the line y equals x. So that means each of these points has to come up over this line, each point. And we want to see what our new line is, and that's going to be the inverse. So now you can imagine it's kind of hard to see this visually. You could count to get the reflection, but the easiest way is to think of it as switching the x and the y values. So basically, if I just write a table of the points that I plotted, so I plotted, I'm just going to do some of them. I plotted -2, 1, I plotted -1, 3, I plotted 0, 5, 1, 7, and 2, 9. So then in order to get the reflection, all you need to do is you just need to switch the x and the y values. So we're just going to switch x and y. So instead of having to count it, if we just switch our tables, so 1, -2, 3, -1, literally just swap in those values. 7, 1, 9, 2. And then if I replot these will actually be the points of the reflection. So we go over 1, down 2, 3, -1, 5, 0, 7, 1, and 9, 2. And when we connect this new line, this will actually be the reflection. So this new line, if you look, it should look like it was flipped over. And the y-intercept is about -2.5, which is what we had, and the slope was up 1 over 2. So here's the new line, which is the inverse function. And so you can see we swapped the x and y values, but really we reflected this black line over the y equals x line. So that's how you find the inverse algebraically and graphically. So let's just look at a couple more examples of those. So here again we want to find the inverse. So we start off by algebraically, we'll set it equal to y. Then we're going to swap x and y. Then we're going to solve for y. So we're going to have x minus 6, as I brought the 6 over, equals negative 3y. Divide everything by negative 3. So we get negative 1/3 x plus 2 equals y. So y equals negative 1/3 x plus 2. Now keep in mind, this is the equation of a line, so it is a function. So I can use this inverse notation to write the inverse. So this would be the inverse function. So let's just do this one graphically and then we won't do any others. You really don't have to do them graphically because really I could get this, and if it said to graph the inverse from this, I could go through this whole process algebraically, get this equation, and then just graph my final answer. But I do want to show you again how to do it graphically. Typically, you can just do it one way or the other. You don't have to do it both unless the directions specify. So algebraically, that's how we did it. Now graphically, we're going to start by graphing the original function. So we have y equals negative 3x plus 6. My slope is negative 3 over 1, so that tells me to go down 3, right 1. Y-intercept is 6, so we're going to start up at 6, and we're going to go down 3, so 1, 2, 3 over 1, down 3 over 1, and really that's enough to be able to get your line, so let's go ahead and connect those. Really you only need 2 points when you graph a line, and we're looking at the table. So I'm going to go ahead, I'm going to label this, and then we'll write our table. So y equals negative 3x plus 6 for this. The table is going to be 0, 6, 1, 3, and 2, 0. And then to get the inverse, remember we're doing the reflection over the line y equals x. So I'm reflecting over this line y equals x. So it should look like it's coming over that line. But the easiest way to reflect is to just take your table and switch the x and y. So we're going to have 6, 0, 3, 1, and 0, 2. So 6, 0, 3, 1, 0, 2. We're going to go ahead and we're going to connect that, and that'll be our inverse function. So it should look as if I took that line and I flipped it over y equals x. And then we just got to make sure we get our arrows and our label on there. We know the equation of this. It has a y-intercept of 2 and it has a slope of down 1 over 3. Down 1 over 3. So this equation is negative 1/3 x plus 2. So let's try one more where we're just going to do this algebraically, and then we'll look at a couple other scenarios. So this next example, again, we start off with a line, so we know that the inverse of it is going to be a function. It's going to be a line. So we're going to take this, and let's just do this one algebraically. We won't worry about doing it graphically. So we're going to first take this, and we're going to set it equal to y. So we have y equals 1/2 x minus 3. We're going to swap x and y. Then we're going to solve it for the new y. So we're going to bring that 3 over, so add 3. We get 1/2 times y. So in order to get rid of the 1/2, you're going to multiply both sides by 2. So just remember, whatever's in the denominator, just multiply everything by that denominator. It'll cancel them out. And just make sure that you distribute that 2 on the left-hand side. So you get 2x plus 6 equals y, or y equals 2x plus 6. And again, I can write this as a function because my original was a function, and because this is a line, any lines are functions. So notice this time too, I put g instead of f of x for the inverse. I only did that because the original was g of x. So that's it. So now this last thing here is saying the horizontal line test. So the horizontal line test is actually used for two things. One, to determine if a function is onto, but it's also to determine if a function, if the function has an inverse that's a function. So a horizontal line intersects the graph of a function more than once, then the inverse is not a function. So if the original function is not one-to-one, that means the inverse will not be a function. So if you look at all of these, my original, so if I look at the original, I can draw any horizontal line through there and it only hits once, which is why the inverse was also a function. So for example, a scenario where this wouldn't work would be if you have like an absolute value function or a parabola. So if I had any parabola and I drew a horizontal line through there, it's going to hit in more than one spot. So the inverse of a parabola or a quadratic will never be a function. So the inverse of a quadratic function will not be a function. So you wouldn't be able to use that function notation for inverses. So basically, if you imagine like if this was on your set of axes, so if these are the x and y axes, if you were to reflect this over the line y equals x, you would see, so if I reflected that, it would look something like this. And you would see that this is not a function because it wouldn't pass the vertical line test. So the inverse of any quadratic would not be a function. Same with anything where you can draw this horizontal line through and it hits twice, it's not going to be a function. So that's something to keep in mind. So for all three of these examples we just done, we started with lines every time. And we know that we can always draw a horizontal line through a line in y equals mx plus b form, and it's going to pass only once. So those are going to be functions. The only time that this wouldn't work is if you started with a horizontal line. If you started with y equals some number, then that wouldn't be, the inverse of that wouldn't be a function because it would be a vertical line. So some other scenarios to look at are something like number 4 here. Number 4 is a cubic function, and we know from our previous unit when we're graphing a cubic function, that means that one end's going to be up, one end's going to be down. And we know that we can use the leading coefficient to determine where we start with this. We can look at the y-intercept. We can find the zeros. So what you could do is you could actually sketch a picture of this going into that 4-step process. I'm not going to go through the whole process, but basically the graph of this would look something like this. So for this function would be a this graph is a function, and the inverse of this graph would be a function. So if this is m of x, I can draw any horizontal line through this, and it's only going to hit once, which means the inverse of this would be a function, which tells me that I can use this notation when I write the inverse. So let's go ahead and do an inverse of something that's not a line, just so you can see how it's similar and how it's different. So we're going to still set it equal to y, so we have 2x to the third plus 1. And we're going to swap our x's and y's. And then we're going to solve it for y. So x minus 1, bringing over that 1. Then we're going to divide everything by 2, because we got to get y by itself. So we have x minus 1 over 2 equals y to the third. And now to undo something that's been raised to the third power is to take the cube root. So we're going to take the cube root of both sides, and we'll end up with y equals cube root of x minus 1 all over 2. but because the vertical or the horizontal line test works for this function, we know that the inverse is also a function, so I can use that inverse function notation. So I can rewrite this using the inverse function notation. And I'm not going to worry about graphing the inverse, but basically it would be a reflection of this curve over the line y equals x. So then the last thing we want to look at in this section is verifying if two functions are actually inverses. So basically we have this property where two functions are inverses if and only if the composition of one function equals x and then the composition of another function equals x. So if I take f of g of x, so if I take g of x and I plug it into f and I get x, and if I take f of x and plug it into g and get x, that means that the functions are inverses of each other. So that's an important property to know, because basically what that's saying is one function's undoing the other to get the input. So let's take a look. So we want to determine if these are inverses. So that means I need to check, does f of g of x equal x, and does g of f of x equal x? That's what I need to see. So first thing we're going to do is we're going to do f of g of x. So you can plug in g of x, because remember we work inside out. So we have 1/2 x minus 1. And then we're going to take that and plug it into function f. So function f is 2x, so I'm going to put parentheses instead of x, plus 1. Replace what's in parentheses with 1/2 x minus 1. And let's simplify this. So distribute that 2. We get x, and we get minus 2 plus 1. So we end up with x minus 1, which does not equal x. So right away I know that these are not inverses, because I already didn't get the first part of what I needed. But just to double check that we didn't make a mistake, what you can do is check the other one. So g of f of x, if we take and we plug in f of x, we would have 2x plus 1. And now we're going to take and we're going to plug this into function g. So we have 2x plus 1, distribute. So we get x plus 1/2 minus 1 gives me x minus 1/2, which does not equal x again. So thus, since these both do not equal x, we know that these two functions are not inverses. And remember, both of them have to equal x. So even if this one equals x, that does not mean that these are inverses of each other. So then we can say, since f of g of x does not equal x, and g of f of x does not equal x, f of x and g of x are not inverses. So that's the conclusion we can make. Now, sometimes it will work where you get f of g of x equals x, and let's say g of f of x does not equal x. You would again have to conclude that they're not inverses.